pleasure to start with Eckart Meiburg from Santa Barbara, who is going to tell us about three-dimensional vorticity dynamics in Hele-Shaw cells.
All right, thank you very much. So I'll briefly go over the motivation for this work, which comes from the area of miscible porous media flows. Then I'll discuss Hele-Shaw flows as a model for porous media flows and show that our simulations show a new splitting instability, what we call an inner splitting instability. We'll discuss the role of stringwise vorticity for that inner splitting instability, and then also the interaction of viscous fingering and density differences. So as I mentioned, the motivation comes from porous media flows, and in particular from oil recovery. So you can imagine when you first discover some oil and you drill a hole, typically the oil is under a lot of pressure, and so it comes out by itself, right? But pretty soon the pressure equilibrates and there's still a lot of oil in the ground. So then what do we do to get the rest of the oil out of the ground? Well, we drill a second hole and we inject some other fluid there, often water or CO2 in liquid form, and we inject it there hoping that we can push the oil out at the production well. So that is schematically shown in this little movie that my student discovered. So we're tapping into the groundwater supply here, taking water out of the groundwater supply and then injecting it into the oil reservoir, which typically is much lower than the groundwater supply. So this black liquid here, that's the oil. So we're injecting the water, and by injecting the water, we push the oil towards the production wells. Well, this is the ideal scenario that the displacement works so nicely, but in reality, it doesn't quite work that well due to an instability that's known as the viscous fingering instability. So the viscous fingering instability is an instability that has been known for a long time to occur when in a porous medium, we have a less viscous fluid pushing against a more viscous fluid. So imagine we're injecting water here into this porous medium and we're trying to push out the oil. You can imagine the oil is very viscous, very sticky. It doesn't want to move really. So you can imagine that as soon as we have a small wavy perturbation here at the interface and the water tends to bypass the oil a bit, this trend will be amplified, and so the water will eventually then form these channels through the oil, bypassing most of the oil, and in that way we still don't get a lot of the oil out of the ground. So this is the viscous fingering instability, which, as I mentioned, can occur when a less viscous fluid displaces a more viscous fluid in a porous medium, or we can also have it if we have a heavier fluid on top of a lighter fluid in a porous medium, then we have a similar instability, a Rayleigh-Taylor type instability, but again in a porous medium. So as I mentioned, this is a well-known instability that has been studied for over half a century, among others here at Cambridge, of course, Phil Safman and G.I. Taylor. People have looked at both immiscible displacements, where a capillary number becomes very important, determines the small-scale cutoff length at the interface, and also more recently, miscible displacements, where we have diffusion and dispersion, and there typically the small-scale cutoff is determined by a Peclet number. So these are the kinds of flows that we're interested in, and what are the governing equations? Well, we have the usual incompressible continuity equation. We have, since we have two different phases or two different fluids, convection diffusion equation for the concentration. But then instead of our typical Euler or Navier-Stokes equations, we now have a different momentum equation, and this momentum equation is called Darcy's law. And it holds for a slow, viscously dominated flow in a porous medium, and what it tells us is that the pressure gradient is proportional to the velocity, it's proportional to the viscosity, and inversely proportional to the permeability. So in other words, the faster the fluid moves, the stronger the pressure gradient, the more viscous the fluid is, the stronger the pressure loss, and the less permeable the porous medium is, again, the stronger the pressure gradient is. What this tells you, and then of course we also have gravitational forces here. What this tells you is that if mu, the viscosity, and k, the permeability of the porous medium, if they are constant, then we have potential flow, and that's of course very interesting, because what that means is that vorticity is introduced in the flow only when we have viscosity changes, permeability changes, or density changes. And that becomes obvious when we reformulate this Darcy's law into a vorticity formulation. Then we obtain this equation here, and that tells us indeed that vorticity is present where we have permeability gradients, where we have concentration gradients that result in viscosity gradients. R here is our ratio of the two different viscosities. And when we have concentration gradients that result in density changes, G here is our dimensionless density difference. So that's something that we should keep in mind, that there are essentially three mechanisms that can create vorticity here: permeability gradients, viscosity gradients, and density gradients.
What's the difference between little k and capital?
Oh, these equations up here are still dimensional, and down here they are dimensionless.
Dimensionless.
Yes. So K is just the dimensionless permeability. So let me just show you such a simulation based on Darcy's law for a simple rectilinear displacement in a porous medium. So this is a case where the two fluids have the same density, and so now we have here the less viscous fluid displacing the more viscous fluid, and you can see how this displacement is unstable, how we form these viscous fingers, and these viscous fingers undergo very interesting nonlinear dynamics. We have here a so-called splitting event. Here's another splitting event. We have merging events. We have a situation where some fingers shield off other fingers from the pressure gradient so that they slow down, and some fingers tend to dominate. So all kinds of interesting nonlinear dynamics, and for that reason, these kinds of flows have been very popular for studying certain pattern generation mechanisms and so on. So that's the basic instability that we're interested in. And as I mentioned, that is very important in practical oil recovery problems. Very often when you fly over an oil field, for example in southwest Texas and so on, and you look down from the airplane, you see these regular arrangements of wells, and often you see this doubly periodic configuration of injection wells here. So that would be where water or some other liquid is being injected, and then in between the production wells, so that's where we're trying to push out the oil. So you can see from this doubly periodic arrangement that we really only have to focus on one such element, and that's called a quarter 5-spot element, and that I have sketched here in 3D. And so we have done some of our studies in these quarter 5-spot elements in order to study these various flow mechanisms and the interaction between the different vorticity modes. This is a situation, a 2D quarter 5-spot, where here we're injecting the water, we're zooming out while we're injecting, so that's how we see these fingers developing. This is a heterogeneous porous medium, so here we generate vorticity both as a result of viscosity differences and as a result of permeability gradients. And then eventually here the water breaks through at the production well, and as you can see, there's still a lot of the black oil in the reservoir left by the time the water breaks through. Here we have a 3D simulation that also shows the effects of gravity. So this is now a 3D quarter 5-spot simulation. Back here along this corner, we inject the water. The water is now supposed to be lighter than the oil, and so you can again see the fingering. At the same time, you can see the so-called gravity tongue forming under the roof of the reservoir, and then eventually again a breakthrough. So very interesting dynamics in these porous media flows, but as I mentioned, the governing momentum equation is now Darcy's law. It's not the Euler or Navier-Stokes equations. Now people would like to study these kinds of mechanisms, of course, from an experimental point of view so that they can get better insight into what's happening. Now, most porous media have the disadvantage that they're opaque, so you can't look inside. So as a result, people are looking for simplified geometries that allow them to study these effects under some simplifying conditions. And the most popular model in that regard is a Hele-Shaw cell. So what is a Hele-Shaw cell? A Hele-Shaw cell is an apparatus that you form when you have two parallel plates right next to each other with a very thin gap in between. The thin gap is typically on the order of a fraction of a millimeter, so it's really quite narrow. And so if you set up an apparatus like this with between two vertical plates, then you have a vertical Hele-Shaw cell. now you can place a heavier fluid on top of a lighter fluid, and you can study the gravitational instability. Or you can take a Hele-Shaw cell, perhaps between two horizontal flat plates. You fill it initially with a more viscous fluid, then you inject a less viscous fluid, and then you obtain this kind of flow here in the cross-section, and then you can develop this fingering instability in the span-wise direction in order to study this viscous instability. So why is a Hele-Shaw cell a good model for a porous medium? Well, if we look at the situation where we have constant viscosity and constant density everywhere, then actually we know from the Stokes flow equations that we have locally everywhere Poiseuille flow. If we gap average across the small direction here over the local Poiseuille flow, then we get for the gap average flow the same momentum equation that we get for a porous medium, namely Darcy's law. So we get again a potential flow for the gap average flow in the presence of constant density, constant viscosity. So that's what I mentioned here. The 3D Stokes equations averaged across the gap direction yield Darcy's law for the 2D gap average flow field, but that's only for constant density and viscosity. Now we're interested in those situations where we don't have constant density and viscosity. We're interested in density differences here to study gravitational instabilities, and we're also interested in viscosity differences here to study viscous fingering. So the question then is, how good a model is a Hele-Shaw cell when we do have variable density and variable viscosity? And that's one of the questions that we're interested in, and that's our motivation for carrying out full 3D Stokes or Navier-Stokes simulations of this flow in a Hele-Shaw cell for variable density and viscosity, and compare with Darcy's law in order to see when do these 3D effects become important. And so in order to answer that question, when 3D effects become important, we did a comparison with experiments for Rayleigh-Taylor instability. So this is now the case of the vertical Hele-Shaw cell. We have a heavier fluid on top of a lighter fluid, and then of course you get an instability along the interface, and you can see here these instability waves, and my experimental collaborators Fernandez, Gorovsky, and Petitjean in Paris, they actually measured in a very nice way dispersion relations for this instability so that they could evaluate growth rates as a function of wave number. So in this case now, the dominant parameter, since there's no superimposed flow, is the Rayleigh number, so essentially a dimensionless density difference, and you can think of it as large Rayleigh numbers corresponding to large density differences and small diffusion coefficients. Small Rayleigh numbers correspond to small density differences and large diffusion coefficients. So we can then compare the experimentally measured dispersion relations for this Rayleigh-Taylor instability in a Hele-Shaw cell with theoretical linear stability predictions based on Darcy's law and based on the full 3D Stokes equations in order to see when do we get good agreement and when don't we? When do we not get good agreement? And so that comparison between these dispersion relations is shown here now. So here we show the linear stability growth rate as a function of the wave number for different values of the Rayleigh number, and we always see the Stokes result in a solid line, the Darcy's result in a dashed line. Down here are the two results for Rayleigh number 100. And we can see that there's actually quite good agreement. So for these very small Rayleigh numbers, which we can think of as large diffusion coefficients, so smeared out interfaces, 3D effects apparently are not very important because the Stokes result and the Darcy result for the dispersion relation are quite close to each other. However, if we increase the Rayleigh number, let's go to 10 to the 4, that's the diamonds here, then this is the Stokes dispersion relation, and this is the Darcy dispersion relation. And now you see there's a substantial discrepancy here, and if we increase the Rayleigh number further to 10 to the 7, then we have down here the Stokes result, up here the Darcy result. So you can see when we increase the Rayleigh number, meaning we reduce the diffusion coefficient, then the interface is sharper, the concentration gradients are stronger, and as a result, this gap averaging no longer leads to a meaningful result, and 3D effects become very important. So for those situations then, we have to say that we should use the full 3D Stokes or Navier-Stokes equations in order to obtain quantitative agreement with experiments in those Hele-Shaw displacements. And so that's what we've then proceeded to do, to carry out some 3D simulations, Navier-Stokes simulations at typically very small Reynolds numbers, less than 1, in order to compare with experiments. So we have here a sketch of our Hele-Shaw cell. We inject our less viscous fluid over here. We assume an inflow Poiseuille profile. We have a convective outflow condition. We take the domain in the spanwise direction of our Hele-Shaw cell as being equal to 1 wavelength of the most amplified wave according to linear stability analysis. And then we have our conventional no-slip solid walls on top and bottom, and here at the spanwise walls we assume that we have slip conditions. Okay, these are the equations that we solve. So the continuity equation, convection diffusion equation, we assume a constant diffusion coefficient here, and as I mentioned, the Navier-Stokes equations now, but for a small Reynolds number on the order of 1. We also need, of course, to define the viscosity concentration relationship, which we assume to be of exponential nature, that matches quite a few fluid pairs quite well. So our dimensionless parameters then are a Reynolds number, a Peclet number, and our viscosity ratio. So let me show you then, well, just for those of you who are interested, a couple of facts on the numerical approach. So we're using third order accurate Runge-Kutta time stepping for the convective terms, and second order Crank-Nicholson for the diffusive terms. We have a fifth order accurate discretization for the convective terms in the spatial direction, and second order central differencing for the diffusive terms. A staggered grid, this is a parallelized code with approximate factorization and a projection method in order to satisfy the divergence equation. So let me show you some results of a first simple simulation. So here we see the finger evolving. This is a crosscut through this center plane, and this is a crosscut through this center plane. And you see this finger develops, this viscous finger. This looks very similar to an experimental observation. But then something interesting happens. We see this hole opening up here in the middle of this finger. So this is not the tip splitting instability that we saw earlier for the Darcy simulation that I showed you, but this is an instability that happens behind the fingertip, and that leads to what we now call this inner splitting. So when we first observed this numerical result, we had a hard time believing it, and so we weren't quite sure what was happening, but we had carefully validated everything. We had carefully validated our code by comparing with linear stability growth rates. All that seemed to be doing fine. All the diagnostic checked out okay. So we're wondering what causes this inner splitting, what causes the appearance of this hole when we plot just one concentration contour. Well, in order to do that, we then take a closer look at the flow field. So let's look again at these two center planes. So this is the situation here with the inner splitting, the 3D concentration contour. Now if we look at, again, this center plane here, so in the middle of the cell, and we look at the C equals 0.5 concentration contour at different times, we see how the finger forms, and then we see how this hole opens up some distance behind the fingertip, while the fingertip itself is still fully intact. If we look at the vertical cross-section in the center of the plane, in the symmetry plane again, so we look at it from the side, then we see this kind of an evolution. And so here we see again now along the center line this pinch-off in the concentration contour, which corresponds to the opening up of this hole here. So if we look at these concentration contours, what that suggests is that apparently there is some of the more viscous fluid from the wall region being convected towards the center plane of the cell. So from the top wall and the bottom wall, it's convected towards the center plane of the cell, and there it seems to pinch off the finger and open up this hole. And that's indeed what is happening. If we look at some other crosscuts, we can see now how that happens. So this is now a top view again. Here we have the concentration contours in the center plane. And let's look now at a few crosscuts at constant x locations. So this is the main flow direction. We're looking first at a crosscut right at the location where the finger is coming through. So that's what we see here. So when the finger tip is first coming through this crosscut, it's essentially like a local source flow. So here the shading indicates the less viscous injected fluid that's coming towards us. And as it's coming first through this plane here, it generates something like a source flow. And so here again, we have within this region the situation where now a less viscous fluid is displacing a more viscous fluid in a source flow-like form. And that leads again to the formation of vorticity, and in particular to the formation of this quadrupole vortex. So we get one vortex that forms here, one vortex that forms here. This is now a crosscut through this region here, and then here a vortex and here a vortex. So we see this quadrupole vortex forming, and this quadrupole vortex now is indeed bringing the more viscous fluid from the top and bottom wall towards the center, and then taking the less viscous injected fluid away from the center in the lateral direction, and in that way it pinches the finger in the middle and leads to the opening up of this hole. And then if we go even further back into this region here, so this is behind even the root of the finger doesn't even start until here, then we see here another quadrupole out here, but that's not so important for our purposes right now. We're mostly interested in what leads to the formation of this hole here. So this is a very interesting observation that we make here, that streamwise vorticity is very important in these Hele-Shaw flows. So even though the gap between these two walls is very, very thin, that does not mean apparently that we can just simply gap average and look only at the two-dimensional flow field within the plane of the Hele-Shaw cell. We do need to pay attention to the velocity and vorticity within the gap, not just the vorticity component perpendicular to the gap. So clearly, these streamwise vortices within the Hele-Shaw cell could not possibly be captured by the gap averaging procedure, because the gap averaging procedure gives us only a two-dimensional flow field and only one component of vorticity normal to the Hele-Shaw cell, whereas we could not get a streamwise component of vorticity out of that. So now I want to show you a few modifications of this situation. Let's look here at a situation where our spanwise domain width is 1.5 times the length of the most amplified wavelength according to linear theory. So now again, we see initially the formation of this finger, but now the cell width is not exactly the right width for just one finger to form, and as a result we see this tendency towards a tip splitting event that we had also seen earlier in the Darcy flow simulations. So now you can see the tip flattens, and then eventually we do get this tip splitting instability here, but then nevertheless we also get the inner splitting behind the tip. So that shows you that these are two very different instabilities. On one hand, the tip splitting instability, on the other hand, the inner splitting instability, and they're being generated in very different ways. The tip splitting instability is something that can be explained just on the basis of this vorticity component. So that's something that can be captured by Darcy's law, whereas the inner splitting requires the streamwise vorticity component, and so that requires a full 3D flow analysis. We can then also take an even wider domain, and now we impose random perturbations, and we can then see the formation of many fingers. So here the domain width corresponds to about 6 times the most amplified wavelength, but we see that initially more than 6 fingers appear. And so that means there's now some competition going on between the fingers, some merging going on here, and some shielding going on. Some fingers fall behind, whereas others outgrow them. And so this now looks very much like a typical experimental observation. And but this is now all based on the 3D Navier-Stokes equations rather than Darcy's law. So we can use these simulations in order to study those nonlinear pattern formations. Now, what was interesting to us is that nobody had ever mentioned this inner splitting instability in the literature, even though people had studied these kinds of flows for a long time. And so we thought, well, what's going on here? So we went back to the experimental literature and actually found this very nice paper by Robin Wooding from 1969. So that's over 40 years old. And he had described this fingering experiment, but he had focused on these tip splitting events and so on. He hadn't paid any attention to what was happening behind the tip. And if you look at it here now, you see behind the tip these long dark regions, which do seem to indicate that something like an inner splitting is happening here some distance behind the tip. So we think that these classical images from these fairly old experiments do give us some support in terms of this inner splitting mechanism that happens way behind the tip rather than the tip splitting on which so much of the investigations since then have focused. Now the situation becomes even more interesting when we also allow for a density difference. So let's imagine now that the injected fluid that we inject from over here is not just less viscous than the resident fluid, but it's also less dense. So buoyancy forces now become important. And so of course we still have the no slip condition at the top and at the bottom. So that means we will still have a thin layer of the more viscous, denser fluid left on each wall. But the finger of the injected fluid is now no longer symmetric with regard to the center line, but it will be uplifted slightly due to buoyancy forces. So you can see the tip here is rising up towards the upper wall. And we're now interested in studying the interaction of the fingering instability with potential gravitational instabilities. Because now you can see along this upper interface here, we have the heavier, more viscous fluid that's left behind on the wall on top of the lighter injected fluid. So that should be an unstable density stratification. And so that has the potential for generating an additional instability. So again, movie to show what's happening. So we have the injected fluid now being a little bit less dense than the resident fluid. And after some time, we see that the first finger is developing. So we do still get this fingering instability in the spanwise direction. But now watch out what's happening here. We have here now an additional instability that's driven by the density difference. So as I mentioned, we have the heavier fluid near the wall on top of the lighter fluid inside the finger. And that leads to the formation of this, what we call an inner cavity, that again bisects the finger in the longitudinal direction. And we did a corresponding linear stability analysis, and the linear stability analysis indeed shows that a typical gravitational instability in the spanwise direction has a shorter wavelength than the viscous fingering instability. And so for that reason, it's not surprising that on top of one viscous finger, we see two wavelengths of the gravitational instability. So if we look again at a crosscut now, so this is the flow after some time. You see here the formation of this inner cavity. If we look at a crosscut here, then we see in white the injected fluid, in dark the resident fluid. And so we now see this instability here in the middle as this negatively buoyant plume that's coming down, bisecting the finger. And of course, it gives rise and it's driven by this vorticity dipole. So we had seen that if we just have viscosity differences, no density differences, then there is a tendency to form vorticity quadrupoles that lead to this inner splitting instability. But now the density difference leads to a Rayleigh-Taylor instability, and the Rayleigh-Taylor instability leads to a vorticity dipole instead. So in some sense we have, yes, in some sense we have a competition here then between a vorticity dipole formation and vorticity quadrupole formation. If we go to the fingertip, so now we look at a crosscut out here, then again, because the fingertip, now the finger fluid is lighter than the surrounding fluid, it tends to rise to the top, and so again that leads to the formation of vorticity dipoles rather than quadrupoles. It's interesting to look at contours of constant vorticity. So here we plot contours of constant streamwise vorticity and constant gapwise vorticity. So that's the vorticity normal to the plane of the Hele-Shaw cell. And we see that these two are strongly correlated. Now, why is that? Well, it's again, if we look at this region here, so we have on one hand the streamwise vorticity being generated by the Rayleigh-Taylor instability. So the Rayleigh-Taylor instability forms this dipole. But then what the Rayleigh-Taylor instability does is it now places the denser, more viscous fluid in between these regions of less viscous fluid. And so that means it now amplifies again the fingering instability, which means that these fluid regions here tend to move faster than the more viscous fluid region in between, and that leads to the formation of this gapwise vorticity. So these two vorticity components amplify each other and lead to this very strong spatial correlation. Okay, then finally a couple of words about what happens in a vertical Hele-Shaw cell. So in a vertical Hele-Shaw cell, we can now inject fluid from below, and we can do that in such a way that we either inject denser fluid from below, in which case the density stratification is stable, or less dense fluid from below, in which case it's unstable, and that again can interfere with the viscous fingering instability. And here already the two-dimensional base flow gives us some interesting topologies. So two-dimensional base flow, that's the base flow just in this direction without the spanwise perturbation. So the two-dimensional base flow can give us some interesting topologies. This is the case of a neutrally buoyant displacement. And so here we plot streamline patterns in the frame moving with the tip of the injected finger. And so in this case, the injected finger is less viscous than the surrounding fluid, which means that it wants to move faster. And so in the reference frame with the fingertip, the oncoming, the fluid, the resident fluid comes towards the finger, and that gives us a sharp stagnation point area here where the concentration front is being kept very sharp. If we take a mildly stable density stratification, so we inject a more dense fluid, then the finger does not want to rise quite so fast, and as a result, in the reference frame moving with the fingertip, the velocity in the resident fluid up here is still pointing in the upward direction. As a result, we now have no stagnation point on the center plane, and we can get this leaking effect of the finger fluid out the top. And then if we have a strongly stable density stratification, then we get again a stagnation point, but now this stagnation point pulls the fingertip apart in these directions, and that can actually lead to the formation of what we call spikes, and that's also something that has been observed experimentally, for example, by Tony Maxworthy. Just one last sequence. So this is now a vertical displacement. So this is the vertical upward direction. I show two fingers so that we can also see clearly the value region in between. The fingers now develop quite nicely, and we'll see again a splitting instability here. But now pay attention to this region down here, where we now have the heavier resident fluid on top of the lighter injected fluid, and we see a Rayleigh-Taylor instability developing down here at the root of those fingers, and that leads to a formation of these anchor-like structures here. So an interesting instability now happening here at the root of the finger, while at the tip of the finger we again see this tip splitting, this inner splitting instability behind the tip. So there are all kinds of interesting things happening, And I just wanted to introduce some of those phenomena that I thought might be of interest to you. So our main interest here is to study these viscous fingering instabilities in Hele-Shaw cells and to look at Darcy versus 3D Stokes flow predictions. What can we learn from gap averaging? When do we need to look at 3D flow equations? We saw the formation of this inner splitting mechanism, which is related to a streamwise vorticity quadrupole. Clearly, that's not something that can be predicted based on Darcy's law, because Darcy's law only gives us one vorticity component, doesn't give us any streamwise vorticity. We looked at the mechanism behind the formation of the streamwise vorticity, and then we also looked at the interaction of these fingering instabilities with density differences. Now, we think there's a whole bunch of open questions here that should be addressed in the future. So what we have looked at so far is only miscible flows, so where we have diffusion. Now, the question is, what happens when we have immiscible flows? We can imagine if there's surface tension around the finger, the surface tension will have a tendency to hold the finger together. So can we still get this inner splitting instability or not? That's an open question. As far as we know, it hasn't been observed experimentally. So perhaps surface tension is always strong enough, but perhaps one could manipulate things through some surfactants and so on to make surface tension weaker, so that even for immiscible flows, we might be able to see this inner splitting instability. Then on another note, what happens if we look at 3D Darcy flows, so 3D porous media flows? Can we have this quadrupole formation and inner splitting appear in those flows? And then also what happens for different types of viscosity profiles? There might be new effects appearing there again. So we feel there's a whole bunch of open questions that still need to be addressed. Okay, thank you very much.
Questions? Yoshi.
So the difference between Darcy equation and the Stokes equation is Laplacian part is just a function itself or something like that. Viscous term is just velocity itself.
Yeah, that's right.
So if velocity satisfies Poisson equation, then both two equation gives the same answer. Do you think so?
No, I don't know exactly what you mean. Maybe that's something we can discuss later. But yeah, it's a different conservation equation, and I don't know what you mean with velocity satisfying the Poisson equation.
Oh, so Laplacian term, Laplacian u,
Yeah.
is if proportional to u. So it's a Poisson equation.
Yes.
So if u satisfies Poisson equation,
Yes.
so Darcy equation and the Stokes equation is just compatible. Right? That is my understanding. Do I understand correctly?
Okay, I'm not sure. That's something I need to think about.
Maybe I missed it at the very beginning. I mean, how is the coupling between the C and the rho?
Well, the density is again a function of the concentration.
Right, that's where's my question. Is that the linear relationship?
Typically, we take a linear relationship, which captures most fluid pairs quite well. But you're right, I should have explicitly pointed that out.
Right, so that is the essential nonlinear coupler, I suppose, if you have, due to the equation for C, right? Because
That's
there
right.
you have the convection while you don't have it in the other equation.
Yeah, so the density difference leads to velocity, which feeds into the concentration
Right.
equation, which affects the density difference again. Bob, yes.
Okay, so there was a period when I was at Eckart where I was part of a group that was studying the cold outflow from a cold weather system that went down the back side of the Rocky Mountains, the west side of the Rocky Mountains. And what we were looking at were the cold tongues of air that went through the passes through the continental divide to the west of Denver and Boulder. And we saw these fingers coming out, not terribly unlike what you have. And these would go unstable like this. We described this in terms of something one of us had called the Humboldt instability, because Humboldt was a professor of his at UCLA many years before.
Yeah.
And there were actually observations of this when the LiDAR people were told where to look.
But these are high Reynolds number flows, right?
These are very high Reynolds number, but they're very highly stratified. So I'm saying
Well,
there's some
Could
similarity.
you ask a question, please?
Well, I just wanted to show, something similar between what you're talking about and dense flows in the environment. It might have more general applicability.
Okay.
Bartek.
Just a quick question. What are the key parameters controlling the time when the inner splitting inaccuracy instability occurs?
That's a good point. So it first is dominated by the Peckley number because towards the end, when you try to accomplish this inner splitting, you need some diffusion so that you can open up this hole. And so the Peckley number is very important. But then in addition, the viscosity difference that governs the strength of this vorticity quadrupole. So that plays an important role as well. But I think it's mostly a function of the Peckley number.
So you decide on a threshold when you call it a gap.
Yes, you look, that's right. You look at a certain concentration contours, and for certain concentration contours, these holes appear at different times.
Answer.
So to follow up on this, is the paucity of experimental evidence perhaps due to the fact that you have to wait quite a bit before these inner gap open?
That could be, yeah.
These were, in some sense, real times you were showing? How do I interpret the time?
Well, that depends on the Peckley number. I think it probably makes more sense in terms of how many gap width has the front propagated before it appears. So in those terms, it was not extremely long. But of course, we had a very clean simulation because we looked at only one finger. So our simulation was not contaminated by the competition among different fingers and merging and shielding, which might overshadow some of this inner splitting in a larger experiment.
Charlie.
In order to study permeability variations, does anyone in experiments use, at least as a toy experiment, Hele-Shaw with varying gap?
Yeah.
Yeah.
People have looked at that. Maybe either wavy gap or etching out some parts of one cell to vary the gap width. So there have been a few experiments like that.
And simulations work well with those? I mean, of course.
I don't think there are any simulations for those things yet.
Well, the last and the quick one. Yuri.
It's not a question, it's short comment. The shape with two filaments looks very often geometry in different flows. For example, in a very fast flows, when a drop falls in a fluid, small drops propagate in the excipient fluid and form two-tailed wake. And very slow vortex line, which go inside the rotating vortex, also have two filament tail with also vortex head. So it looks like very stable geometrical construction.
The last comment that I would like to make is that the paper I read about Hele-Shaw flows the first time was RF. So we should perhaps make
That's true. Yes, that's true. Hassan has pioneered
exposition of the Hele-Shaw problem.
That's right, and he has pioneered the use of vortex methods for immiscible Hele-Shaw flows, and so he made a great contribution there. Yeah.
Thank you very much.
Thank you.